Hello everyone, I'm here to give a presentation on deep learning project. Here are the contents of my presentation. The first, we are going to talk about the use of TensorFlow directly in coding, and the part two is data sets of image or audio, and the third part is how to obtain a DF CIFAR 10 data set for the project. Then part four is how to build, train, and test convolutional neural network on the data set, on the CIFAR 10 data set. 5, we are going to compare the convolutional neural network performance. And then 6, improve on the convolutional neural network performance. The final part will be to discuss about the project report. In this course, we are required to carry out a project using a TensorFlow, and every student is required to use a TensorFlow directly in coding instead of using Keras and other deep learning frameworks, because TensorFlow has a good support and good compatibility for most of the data sets. So we are going to use TensorFlow version 1.15 for this analysis. And every student is required also not to just to use TensorFlow and not Keras for this project. In this part 2, we are required to get a data set of images or audio files from any good source, and this is the data set I got from Google Data Search. Is about optical coherence tomography for image-based deep learning. Is optical coherence tomography, and this is a non-invasive imaging technique. In this data set, we have 1,600 high-resolution grayscale images of retinal structure, which are labeled according to disease group and retinal pathology. This OCT is an important tool for early diagnosis of ocular condition and detection of retinal diseases, and is a very good data set for image recognition. The data set was obtained from this link through Google Data Search, and is available for public use. The data set has 6 categories, and also they are all labeled images. Here are the categories. One is the age-related macular degeneration. These are more of medical terms, but they are well labeled for this image recognition. On a TensorFlow. And the first one has about 885 images. The second one has about 22 images. And then the diabetic macular edema has about 143 images. Then the normal images and 93 images of retinal artery occlusion. The data sets are well labeled and they are shown. This is the example of the data sets, the screenshots of the data set as they are uploaded on the site. Here are the file names. They are well labeled. This is the label name, and here are the names of the files, and these are the diseases that are labeled, and it has other categories, has other features on it. but we are more interested in the file name and the particular disease. And then the part 3 of this project, we are required to obtain a CIFAR 10 datasets, and also how to upload this on a remote server after downloading the dataset from the canvas. We are required to upload it to our GCP account for the analysis and for TensorFlow. The reason why we are not using our personal computer is because of the stability issues and also memory issues. These are very big data sets, and also running TensorFlow takes a lot of computation power. So after uploading the data set on a Google Cloud platform, we'll start a remote virtual server instance. And then we create a new folder, a new subfolder with this name, CIFAR 10 data, to upload this data set from the canvas into the remote virtual server. And we do that by using this command line, make a directory. And then we run this command to copy the data file to the new subfolder. There are many files, there are about 7 other files in this CIFAR 10 data. So we use the same command line to upload all the data into this new subfolder. And then here we are going to build and train, then test our convolutional neural network, our CNN, on this CIFAR 10 data sets. And the design of this model includes different layers of convolutional layer, and then we have the pooling layer, then the ReLU, and then the ReLU layer. Here the shape of the 4D shape of the 4D shape of the image is a 100 by 32 by 32. This means the batch is 100, and then height is 32, the width is 32, and this is the depth of the image, which is a 3, and this 3 is for color, is for RGB color. And this is the shape of the 2D data that are uploaded into the CNN. Is 32 by 32. It means is 32 height and 32 width. We input and this is the input shape with 3 inputs, depth in channel color, and this for RGB color. 3 is for RGB, which means red, green, blue color. And then the output shape will be 32 by 32 by 32, and the depth of the output channel is 32. Then we use for this case, we are going to use a 3 by 3 filter instead of 5 by 5. And because 3 by 3 requires a little computation instead of using 5 by 5, because this data set is very big, and also because it requires a lot of computation power. So there is no need using a 5 by 5 for this CNN. So the filter shape is here is the filter shape is 3 by 3, 3, and then 32. Stride, we are going to use 1 for the stride. The stride 1, it enables the filter to move 1 pixel at each time. It enables the filter to move 1 pixel at each time. And this is the shape of the stride. Here we use padding same. for all the convolutional neural layers, for all our layers, convolutional layers in this project. Why we want to use padding same is in order to make the spatial dimension of the input to preserve the spatial dimension of the input. And here we are going to use the ReLU function, ReLU activation function, to introduce linearity the image into the convolutional neural network. And then here, this is the ReLU layer 1. Here we don't need any filter because we only process the data, no need to extract features or learn features. And the input shape is 32 by 32. Also the same with the output shape. And then for the convolutional layer 2, we also have a shape, the badge, the height, and the width, which is 116 by 64. And this is the 2D data side for the image. Here we have an input shape of 16 by 16 by 32, and then the depth of the depth input depth is 32 channel for color, and then 64 out channel. And also we keep the same filter size 3 by 3 because for this filter is good for these big data sets, for color data sets, because